66 million years ago, the world was alive in a way we can barely imagine. Not alive like today. Alive in a different register entirely. Louder, heavier, more ancient, and more strange. The air was warmer by 8 to 10 degrees Celsius compared to our present. The seas ran higher. The forests stretched without interruption across continents that looked nothing like the maps on your wall. And everywhere, from the swamps of what would become Montana to the river deltas of what would become North Africa, the ground shook beneath the weight of creatures that had ruled this planet for 165 million years. Think about that number for a moment. 165 million years. Homo sapiens, our entire species, has existed for roughly 300,000 years. The Roman Empire rose and fell in less than 1,000. Everything we call human civilization fits inside 12,000 years. And yet the dinosaurs walked this earth for a span of time so immense that if you compressed all of it into a single 24-hour day, human history wouldn't even register as the final half-second before midnight. They were not a failed experiment. They were not primitive. They were not slow, cold, stupid creatures waiting to be replaced by something better. By the late Cretaceous period, the world we are about to enter, dinosaurs had evolved into forms of breathtaking sophistication. Tyrannosaurus rex had a bite force of over 35,000 newtons, stronger than any land animal before or since. Triceratops carried a skull that weighed as much as a small car. Alamosaurus, a titanosaur sauropod browsing in what is now Texas, stretched over 29 meters from nose to tail and weighed somewhere between 60 and 70 metric tons. Quetzalcoatlus, the flying reptile that soared above them all, had a wingspan of 10 to 11 meters, the size of a small aircraft, and stood as tall as a giraffe when it walked the ground. This was their world, and on one specific morning, 66 million years ago, every single one of them woke up as they always had, as their ancestors had for millions of years before them. Completely unaware that somewhere above the curve of the Earth, traveling at roughly 20 kilometers per second, a rock roughly 12 kilometers wide was closing the distance between itself and this living, breathing, thundering world. This is the story of those last 24 hours. Not as a disaster film, not as a cartoon extinction, but as a scientific reconstruction, built from the fossil record, from geochemical analysis, from impact physics, from paleoclimatology, from the thousands of researchers who have spent their careers piecing together the most consequential single day in the history of complex life on Earth. We know what morning looked like. We know what the skies were doing. We know what the animals were eating, where they were sleeping, how the temperature sat on the air. We know, with extraordinary precision, what happened in the seconds after impact, in the first hour, in the first day, in the first year. And we know exactly what never happened again. So let's go back. 66 million years ago, late Cretaceous, the Hell Creek Formation, a vast floodplain system stretching across what is now Montana, North Dakota, South Dakota, and Wyoming. It is early morning. The light is just breaking over a landscape that feels subtropical even by today's standards. Dense vegetation, shallow rivers braided across a wide alluvial plain, the air thick with humidity and the smell of flowering plants, which are themselves still a relatively recent evolutionary innovation on this planet. A group of Edmontosaurus, large hadrosaurs, duck-billed dinosaurs weighing up to 4 tons each, are already moving through the tree line at the river's edge. They move in a loose herd. They have been moving since before first light, as they often do, instinctively avoiding the hours when large theropods are most active. Their footfalls leave deep oval impressions in the soft mud, impressions that, in some locations across North America, are preserved to this day. They are eating, they are breathing, they are alive. They have no idea. And neither 66 million years later did the geologist Walter Alvarez when he stood in a limestone gorge near the Italian town of Gubbio in 1977, staring at a thin, rust-red layer of clay sandwiched between two bands of white rock. Below the clay, marine fossils from the Cretaceous, rich and diverse and abundant. Above it, almost nothing. A silence in the rock that lasted millions of years. That thin layer of clay would eventually be found at over 300 sites around the world. It contains iridium, an element rare in Earth's crust, but common in asteroids, at concentrations 100 to 1,000 times higher than normal. It contains shocked quartz, grains of silica that only form under pressures of tens of gigapascals, the kind generated by hypervelocity impact or nuclear detonation. It contains spherules of glass, tiny droplets of rock that were melted, hurled into the atmosphere, and rained back down across the entire planet. That layer is called the KPG boundary, the Cretaceous-Paleogene boundary, and it marks, with geological precision, the single worst day in the history of animal life on Earth. Everything below it, a world dominated by dinosaurs. Everything above it, a world that would eventually become ours. But before we get to what ended that world, before the fire, before the darkness, before the cold, we need to spend time in what was lost. Because the story of that last day is not just a story about destruction. It is a story about a world at the absolute height of its complexity, its diversity, its evolutionary richness. A world that, on the morning of that final day, had every reason to believe it would last another 66 million years. Let's find out what it looked like when it was still alive. To understand what was lost, you have to understand what existed. And what existed 66 million years ago was not the world of Jurassic Park, not the world of the original 1993 film, that vision of green, primordial jungle populated by smooth-skinned, lizard-brained monsters moving through perpetual mist. The late Cretaceous was something altogether more complex, more colorful, more ecologically intricate than anything Hollywood has ever put on screen. Start with the geography. The continents in the late Cretaceous were arranged in a configuration that would be unrecognizable to us today. North America was divided down its middle by a vast inland sea, the Western Interior Seaway, stretching from the Arctic Ocean in the north all the way to the Gulf of Mexico in the south. It was a warm, shallow body of water, nowhere much deeper than 900 meters, teeming with mosasaurs, plesiosaurs, enormous fish, and ammonites the size of tractor wheels. It effectively split the continent into two separate land masses, Laramidia to the west and Appalachia to the east. Europe was not Europe. It was an archipelago, a scattered chain of tropical islands sitting in a warm, shallow sea, something like an ancient version of the Indonesian archipelago today. India was not attached to Asia. It was an island continent, drifting northward through the Tethys Ocean at a rate of roughly 15 to 20 centimeters per year, carrying its own isolated fauna that had been evolving in separation for tens of millions of years. Antarctica was not frozen. It was warm enough to support forests and fauna, connected at various points to South America, and home to dinosaurs whose fossils we are still finding today. Africa and South America had separated, but only recently in geological terms, and both still retained echoes of the fauna they had shared when they were a single landmass called Gondwana. The Earth, in other words, looked like a completely different planet. And the climate matched. There were no polar ice caps. Temperatures at the poles were cool, perhaps similar to modern-day Scotland or southern Canada, but not frozen. The equatorial regions were hotter and more humid than today. The global average surface temperature was somewhere between 4 and 10 degrees Celsius warmer than our present. Sea levels were higher by roughly 80 meters. The atmosphere contained somewhat more carbon dioxide than our pre-industrial baseline, creating a mild but persistent greenhouse effect that kept the planet warm from pole to pole. What this produced was extraordinary biodiversity. In the Hell Creek ecosystem alone, the one we are using as our primary window into that last day, paleontologists have identified dozens of dinosaur species. Tyrannosaurus rex, of course, Triceratops and its close relative, Torosaurus, whose three-horned skull still generates fierce debate about whether they represent two species or two growth stages of one. Ankylosaurus, the armored giant whose clubbed tail could shatter the leg bones of a tyrannosaur. Edmontosaurus and Triceratops dominated the herbivore niche the way elephants and wildebeest dominate the African savanna today. But it wasn't just the famous names. There were pachycephalosaurs, small bipedal dinosaurs with domed skulls up to 25 centimeters thick, used in headbutting contests that biomechanical studies suggest could generate forces comparable to a car crash at moderate speed. There were small theropods, feathered and fast, filling the ecological roles that hawks and foxes fill today. There were enormous crocodilians in the rivers, mammals in the undergrowth. Small, furtive, mostly nocturnal, looking nothing like the mammals that would inherit the Earth, but carrying inside their genomes the blueprint for every living thing with fur that exists today. Above all of it flew pterosaurs, Quetzalcoatlus northropi, the largest flying animal in Earth's history, is worth pausing on for a moment because it consistently defies belief even among paleontologists who have spent their careers studying it. Described formally in 1975 from material found in Big Bend National Park in Texas, it had a wingspan estimated between 10 and 11 meters. It weighed, according to the most widely accepted current estimates, somewhere between 200 and 250 kilograms. It stood on the ground approximately 5 meters tall at the shoulder, eye level with a large giraffe. For decades, researchers debated whether something this size could actually fly at all. The numbers seemed impossible. An animal that heavy, with a body that large, should not have been able to generate the lift required. But biomechanical modeling published over the last 2 decades has consistently shown that Quetzalcoatlus almost certainly could fly, and probably was an extraordinarily efficient long-distance soarer, using thermal columns of rising warm air to cover vast distances with minimal energy expenditure, much like a modern condor scaled up to terrifying dimensions. On that last morning, they were in the air, riding the thermals above the Hell Creek floodplain, looking down at a world that had no idea it was about to end. And that world was not uniform. It was not a single static ecosystem. The late Cretaceous was a planet of profound ecological diversity, not just between continents, but within. The Hell Creek environment alone shifted between river channels and floodplains, dense forests and open coastal plains, swampy lowlands, and slightly elevated drier terraces. Different species occupied different niches within this mosaic. Triceratops favored the more open, drier areas. Evidence from their tooth wear, analyzed using stable carbon isotope ratios, suggests they were primarily browsers of low-growing flowering plants. Edmontosaurus, by contrast, with its distinctive dental battery, a structure containing literally hundreds of teeth packed into a grinding surface, likely favored softer, more aquatic vegetation near river margins. Tyrannosaurus rex moved through all of it. And it is here, with the apex predator of the Hell Creek ecosystem, that we need to spend a moment, because the Tyrannosaurus rex of 66 million years ago was not the Tyrannosaurus rex of your childhood. Science has not stood still. The image of that animal has been revised, refined, and in some respects, completely overturned over the last 30 years. And to understand what was lost when that asteroid hit, you need to understand just how sophisticated, how biologically complex this animal actually was. The debate about T-Rex's appearance has been slowly settled in favor of something more unsettling than the smooth-skinned version from cinema. Patches of fossilized skin impressions from T-Rex, rare but confirmed, show large scales on portions of the body. However, research published in journals including PeerJ has pointed out that the scale impressions found so far represent only specific body regions, and that the dorsal surface, the back, the neck, the arms, may well have carried some degree of feathering or filamentous covering, particularly in juveniles. The picture is still not fully resolved, but the consensus has shifted firmly away from a purely scaly animal. Its brain, as revealed by CT scanning of endocasts, the impressions left inside fossilized skulls, was proportionally large for a theropod of its size, with particularly enlarged olfactory bulbs, meaning its sense of smell was extraordinary. Some researchers have compared its olfactory capability, in relative terms, to that of a modern turkey vulture, an animal capable of detecting a carcass from distances of several kilometers. Its vision faced forward, like a hawk's or an owl's. This configuration, preserved in skull anatomy, suggests stereoscopic depth perception, the ability to judge distance accurately, the kind of visual system you evolve if you hunt by active pursuit and need to judge the exact moment to strike. It was, by every metric we can apply, not a monster. It was a supremely functional biological machine shaped by 165 million years of evolutionary refinement. It had warm blood, almost certainly. It grew fast, reaching near adult size in roughly 20 years. It lived for perhaps 30 years or more. It probably had some form of parental behavior, though the evidence for this remains incomplete. On the morning of that last day, there were Tyrannosaurus individuals somewhere in the Hell Creek floodplain system doing what they did every morning of their lives: moving, hunting, watching, smelling the air. They shared this world with creatures equally extraordinary on every other continent. In what is now South America, abelosaurid theropods prowled ecosystems that looked nothing like Hell Creek. In what would become India, titanosaur sauropods of staggering size left footprints that we still find today in the Lametta Formation. In Europe's island archipelago, dwarf dinosaurs had evolved in isolation, a phenomenon called insular dwarfism, where large animals on islands evolve smaller body sizes over generations due to limited food resources. Rhabdodon and Zalmoxes browsed through subtropical forests on islands that would eventually become France and Romania. All of them on that last morning were simply living. That is the thing that the fossil record asks us to sit with, and that cinema consistently fails to capture. The moment before the impact was not dramatic. It was ordinary. It was another morning in a world that had been running uninterrupted for 165 million years. The Edmontosaurus were feeding. The pachycephalosaurs were competing for mates. Somewhere in the forests, small mammals were sleeping through the daylight hours in burrows, waiting for darkness. The mosasaurs were hunting in the western interior seaway. Quetzalcoatlus was soaring on a thermal above the river plain. The world was doing what it always did. And then In the sky above what is now the Yucatan Peninsula in Mexico, something entered the atmosphere. It had been traveling for billions of years. It was a fragment of a much larger body, a carbonaceous chondrite, or possibly an ordinary chondrite, its exact composition still debated, that had been drifting in an elliptical orbit around the Sun since before the Earth itself existed. It measured, best current estimates suggest, somewhere between 12 and 15 kilometers in diameter. Some researchers put it as large as 17 kilometers. For perspective, that is wider than the city of London, taller than the summit of Mount Everest above sea level. It entered the atmosphere at an angle of approximately 45 to 60 degrees to the surface, an angle that, according to impact modeling published in the journal Geophysical Research Letters, maximized the destructive footprint of the event. A steeper angle would have concentrated the damage. A shallower angle might have caused the impactor to skip back into space. But at 45 to 60 degrees, the energy release was spread across a vast area of the atmosphere, seeding the entire sky with superheated material. It was moving at approximately 20 kilometers per second. That is 72,000 kilometers per hour. In the time it takes you to read this sentence, it had already closed a distance of roughly 40 kilometers. The dinosaurs in the Hell Creek floodplain were thousands of kilometers from the impact site. They had perhaps 45 minutes from the moment of impact before the first effects reached them. In that time, they would continue to feed, to move, to breathe. But something was already ending. Above the clouds, invisible to every living thing on Earth, the last sunrise of the Cretaceous was already beginning to lose its meaning. Let's establish the timeline precisely, because precision matters here. The impact did not happen at a vague mythological moment outside of time. It happened on a specific day at a specific hour, and the sequence of what followed unfolded according to physics that we can calculate, model, and verify against the geological record with remarkable accuracy. The impactor hit what is now the northern coast of the Yucatan Peninsula at a location we call the Chicxulub crater, named after a small town near its center. The crater it produced is roughly 180 kilometers in diameter and 20 kilometers deep at its center. It is one of the largest confirmed impact structures on Earth, and thanks to decades of drilling, seismic imaging, and geochemical analysis, including the landmark IODP-ICDP drilling expedition of 2016, which extracted cores from the crater's peak ring, we know more about this impact than about almost any other event in deep geological time. What we do not know with certainty is the exact time of day it struck, but we have clues. Research published in 2022 in the journal Scientific Reports, led by paleontologist Melanie During and her colleagues, analyzed the fossilized remains of paddlefish and sturgeon found at the Tanis site in North Dakota, a site we will return to in detail because it is the single most extraordinary geological deposit ever found in relation to this event. The fish at Tanis died within the first hour of the impact. Their bones show annual growth rings, like tree rings, and the position of those rings at the time of death indicates they were killed in spring, specifically late spring in the northern hemisphere. Other research examining the chemistry of fossilized plant material from the KPG boundary has produced consistent results pointing to spring or early summer. So, late spring, northern hemisphere morning, most likely, based on the angle and trajectory modeling of the impactor. The exact hour is still debated, but several researchers have noted that the geological evidence from the Tanis site, which we will examine closely, suggests the shock wave and the resulting seismic event reached North Dakota while animals were actively feeding, which in a late Cretaceous ecosystem of that latitude would be consistent with morning hours, Let us say morning. Let us say late spring. 66 million years ago. A warm morning in late spring. The last spring that would ever belong to the Cretaceous. 6 hours before impact. In the Hell Creek floodplain, the morning is already well advanced. The light has the quality of subtropical late spring, bright but slightly hazy with humidity, the air carrying the smell of river mud and the strange resinous scent of the conifer forests that line the higher ground to the west. The flowering plants, angiosperms, a relatively recent evolutionary arrival, are in bloom along the riverbanks. The world smells alive. The Edmontosaurus herd has moved deeper into the tree line. 2 large females stand at the river's edge, drinking. Their reflections move on the water's surface. One of them lifts her head. 360 kilograms of skull moving upward on a muscular neck, and scans the opposite bank. Nothing there. She returns to drinking. A juvenile Triceratops, perhaps 4 years old and already the size of a large horse, is browsing in the low vegetation at the forest edge. Its frill, that extraordinary structure of bone and keratin that paleontologists now believe function primarily in visual communication and species recognition, based on research including work published in Proceedings of the Royal Society B, carries a flush of color that we cannot know precisely, but that almost certainly varied between individuals and changed with mood and arousal state, much as facial coloration changes in living horned lizards today. The juvenile is alone. Not entirely unusual. Juvenile Triceratops are sometimes found in what appear to be solitary deposits in the Hell Creek Formation. But it is alert. Its eyes, positioned laterally on the skull, giving a wide field of view, sweep the forest edge every few seconds. It has reason to be alert. Approximately 300 meters away, partially concealed by the shadow of a large conifer, a subadult Tyrannosaurus rex is watching it. This animal is roughly 15 years old, still growing, but already enormous. Perhaps 7 meters long and weighing close to 3 tons, not yet at the full adult size that the largest T-Rex specimens suggest could reach 12 to 13 meters and 8 to 9 tons, but already capable of killing prey far larger than itself. Its binocular vision is locked on the juvenile Triceratops. It has been watching for roughly 12 minutes. It is calculating. Not in any conscious sense, but in the deeply evolved, neurologically sophisticated sense of a predator that has been refined by evolution into a machine for making exactly this kind of decision. It does not move yet. 4 hours before impact. Across the western interior seaway, a different kind of morning is in progress. The seaway at this latitude is calm. The weather over the interior of North America in the late Cretaceous was influenced by the warm, shallow waters of the seaway itself, generating humid, semi-tropical conditions across Laramidia. Near the surface, schools of large teleost fish, Zephactinus, a formidable predatory fish reaching up to 6 meters in length, are hunting. Their prey, smaller fish and ammonites, dart and scatter in the clear, warm water. Below them, moving slowly along the bottom in approximately 40 meters of water, is a mosasaur. Mosasaurs are worth a moment of our time because they are among the most successful marine predators in the history of vertebrate life, and they are almost never given the attention they deserve. They were not dinosaurs. They were squamates, closely related to monitor lizards and snakes, that returned to the sea in the early Cretaceous and, over approximately 30 million years, evolved into the dominant marine predators of the late Cretaceous oceans. By 66 million years ago, they had diversified into dozens of species occupying every marine niche from shallow coastlines to open ocean. The largest of them, Mosasaurus hoffmanii, reached lengths of 17 meters or more. Its jaw mechanics have been studied using CT imaging and finite element analysis, and the results are extraordinary. It had two sets of teeth, one on the main jaw margins and one on the roof of the mouth, meaning that prey that escaped the first bite would be caught by the second. Its tail was not the simple paddle it was depicted as in early reconstructions, but a forked, shark-like structure. Evidence preserved in phosphatized soft tissue remains from exceptional Cretaceous deposits in Kansas that would have made it a faster, more agile swimmer than previously imagined. The animal in the seaway this morning is a prognathodon, a large, robust mosasaur with particularly massive crushing teeth designed for hard-shelled prey. It is moving languidly, conserving energy. It has eaten recently. Above it, the surface of the sea catches the morning light in long, slow ripples. It has no concept of the rock currently crossing the orbit of the inner solar system at 20 kilometers per second. 2 hours before impact. The subadult Tyrannosaurus in the Hell Creek forest has made its decision. It moves. The acceleration of a tyrannosaur from a standing start has been modeled using biomechanical simulations based on muscle attachment scars, bone cross-sections, and comparisons with living bipedal animals. The results, published by researchers including William Sellers at the University of Manchester, suggest that adult T-Rex was not a fast runner. Maximum speeds are estimated at somewhere between 17 and 25 kilometers per hour for fully grown adults, and some models suggest even lower top speeds due to the immense bone stress that higher speeds would have generated. But the subadult, lighter and proportionally more agile, could likely reach higher relative speeds. More importantly, it is not trying to run down the juvenile Triceratops. It is trying not to be seen until the last possible moment. The juvenile Triceratops sees it anyway. What follows is not a neat, cinematic confrontation. The fossil record of theropod ceratopsian interactions in the Hell Creek Formation, preserved in bone pathologies, healed bite marks, and the occasional direct association of remains, suggests that these encounters were frequently inconclusive. Triceratops was not easy prey. Its neck frill, while not impenetrable, provided some protection to the throat. Its horns, the nasal horn and the two long brow horns, which in adults could reach over 1 meter in length, were not decorative. Studies of bone surface texture and horn morphology confirm they were genuine weapons capable of inflicting serious injury. The juvenile charges. Not at the tyrannosaur, away from it, crashing through the low vegetation toward the river where the herd of Edmontosaurus is already scattering at the commotion. The subadult tyrannosaur pulls up. It watches the juvenile disappear into the undergrowth. It stands at the forest edge for a moment, nostrils working, processing the scent information in the air, and then turns away. There will be other opportunities. There always have been. It has no way of knowing there will not be many more. 1 hour before impact. The sky above the Yucatan Peninsula looks like any other sky on any other late spring morning. Blue. High cirrus clouds in thin scattered streaks. The sun already climbing toward midday. The warm green smell of the coastal forests. The sound of waves. The impactor is no longer in space. It entered the atmosphere, what there is of the atmosphere at extreme altitude, approximately 30 seconds ago. At that altitude and at that velocity, the distinction between atmosphere and vacuum is almost academic. The rock is not slowing appreciably. It is not burning up the way a smaller meteor would. It is punching through the thin upper atmosphere the way a bullet punches through tissue paper, barely noticing it. But the air in front of it is being compressed to temperatures exceeding 20,000 degrees Celsius. The plasma sheath forming around the leading edge of the impactor is brighter than the sun. Any living thing within line of sight of that entry corridor, across a significant arc of the western sky from the perspective of North America, would have seen a light unlike anything in nature. A streak of impossible brightness moving across the sky at a speed the eye could barely track. There are no human eyes to see it, but there are eyes. Somewhere in the Hell Creek floodplain, an animal looks up. We do not know which animal. We cannot know. But animals notice unusual light. They notice unusual sound. The very upper edge of the sound generated by the impactor's passage through the atmosphere, infrasound, frequencies below human hearing but detectable by many animals, may have reached the Hell Creek region even before the impact itself. 30 seconds before impact. The impactor is 40 kilometers above the surface of the Yucatan Peninsula. It is still moving at effectively its entry velocity. The atmosphere has slowed it by perhaps a fraction of a percent. It is 12 to 15 kilometers wide. Its leading face is a wall of rock and plasma traveling at 20 kilometers per second. Beneath it, the limestone platform of the Yucatan, built up over millions of years from the compressed remains of marine organisms rich in calcium carbonate and, critically, rich in sulfur-bearing minerals called evaporites, is about to experience forces it was never built to withstand. 10 seconds. The compression wave ahead of the impactor hits the surface. Even before the rock itself makes contact, the atmospheric pressure at ground zero exceeds anything that exists anywhere on Earth under normal conditions. The vegetation within the immediate impact zone, the trees, the ferns, the flowering plants, the insects, the small animals, ceases to exist as biological matter. It is converted in microseconds into component atoms by forces that have no comparison in everyday experience. 5 seconds. The impactor's leading edge contacts the limestone. What happens next is not an explosion in any conventional sense of the word. It is something that requires a different vocabulary entirely. The kinetic energy released in the first second of contact has been calculated at approximately 100 million megatons of TNT, roughly 10 billion times the energy of the atomic bomb dropped on Hiroshima. In the first microseconds, the impactor and an equivalent volume of target rock are vaporized simultaneously. Not melted, not shattered, vaporized. Converted directly from solid matter into superheated plasma at temperatures of tens of thousands of degrees. The rock beneath the impactor does not simply give way. It accelerates downward at thousands of meters per second as the impactor drives into the crust. In the first second, the crater is already several kilometers deep. Rock that was solid limestone milliseconds earlier is behaving like a fluid, flowing outward and downward, and then, as the pressure wave rebounds from depth, flowing back upward in a temporary mountain of liquid rock at the center of the impact site, taller than Mount Everest, that will collapse back down within minutes. The sound of this event has no analog. At ground zero, there is no sound. There is no medium to carry it. The air itself has been swept away by the initial energy release, replaced by an expanding sphere of superheated plasma. The silence at the center of the Chicxulub impact lasts for a fraction of a second, and then it is replaced by something that is no longer sound in any biological sense. It is the planet screaming. 1,200 kilometers away, in the Hell Creek floodplain, the Edmontosaurus are still standing in the river shallows. They have 45 minutes. 0 minutes after impact. The crater at Chicxulub is still forming. This is important to understand because the mind instinctively wants to treat the impact as an instantaneous event, a single moment of contact and then aftermath. But the physics of a hypervelocity impact at this scale unfolds over minutes, not milliseconds. The crater does not exist yet in any final sense. It is a process, a wound in the planet's crust that is still opening, still deepening, still propagating outward at velocities that dwarf anything in ordinary geological experience. In the first 2 minutes after contact, the transient cavity, the initial hole punched by the impactor, reaches a depth of approximately 30 kilometers and a diameter of perhaps 100 kilometers. The rock at this depth is no longer behaving like rock. Under pressures of hundreds of gigapascals, the Earth's crust is flowing like water in slow motion. The walls of the cavity are collapsing inward and downward. The central uplift, that temporary mountain of liquefied rock that surged upward as the impactor drove in, is already beginning to collapse under its own weight, generating a secondary wave of destruction that radiates outward from the impact center like a ripple in a pond. Except that this ripple is made of molten rock and is moving at hundreds of meters per second. The final crater shape, 180 kilometers wide, with its distinctive peak ring of uplifted rock, will not stabilize for several more minutes. By the time it does, an estimated 48,000 cubic kilometers of rock and sediment will have been excavated, vaporized, melted, or ejected into the atmosphere and beyond. Some of that material is going to leave the atmosphere entirely. Small fragments of rock accelerated to velocities exceeding Earth's escape velocity of 11 kilometers per second will be launched into space. Some of them will eventually fall back to Earth. Some of them, over the coming thousands of years, will reach the Moon. Some small fraction will eventually reach Mars. The Chicxulub impact scattered debris across the entire inner solar system, but most of what was excavated stayed closer to home. 3 minutes after impact. The ejecta curtain is the term scientists use for the expanding ring of material thrown outward from an impact site at high velocity. At Chicxulub, the ejecta curtain is unlike anything the Earth has experienced in hundreds of millions of years. It consists of rock fragments ranging in size from microscopic dust to boulders several meters across, all moving outward at velocities of several kilometers per second, many times the speed of sound. At distances up to several hundred kilometers from the impact site, this ejecta arrives as a wall of supersonic rock and is instantly lethal to everything in its path. The forests of what is now the Yucatan, Guatemala, and surrounding regions are scoured from the surface. The coastal areas are hit simultaneously by the ejecta curtain and the first pulse of an impact-generated mega tsunami. A wave whose initial height near the impact site is difficult to calculate with precision, but which modeling suggests may have exceeded 1 kilometer in the deep water of the Proto-Caribbean. At greater distances, the ejecta arrives differently. The finest material, the glass spherules, the microtectites, the dust, is lofted into the upper atmosphere and stratosphere, where it will begin a journey that will take it around the entire planet within hours. These are the tiny glass beads that geologists find today at KPG boundary sites on every continent. Each one is a frozen droplet of Yucatan limestone, melted in an instant 66 million years ago, and then flash frozen by the cold of the upper atmosphere as it arced upward and began to fall back down. But there is also something in between the dust and the boulders, something that most popular accounts of the Chicxulub impact fail to mention, and that turns out to be one of the primary kill mechanisms for animals thousands of kilometers from the impact site. Incandescent ejecta. Glowing hot rock fragments, the size of small stones, re-entering the atmosphere at high velocity from above. Think about what that means. The material ejected at Chicxulub was launched at such velocity that it went above the atmosphere. It followed ballistic trajectories through space before falling back to Earth, and when it re-entered, not at any single location, but distributed across the entire hemisphere visible from the impact site. It did so at high velocity, creating frictional heating with the atmosphere. Multiplied by trillions of individual particles falling simultaneously, this re-entry heating had a cumulative effect on the upper atmosphere that researchers have compared to the setting of a global oven. The physicist and impact researcher Brian Toon and his colleagues, in work published over several decades, calculated that the thermal pulse from re-entering ejecta would have been sufficient to ignite fires across vast areas of the northern hemisphere within roughly 45 minutes of the impact. Not from the direct heat of the impact itself, but from the sky, literally glowing with re-entering debris, radiating heat downward like a planetary broiler. This is the mechanism that reaches Hell Creek, 45 minutes after impact. Let's be precise about what the animals in the Hell Creek floodplain experience, because this is where the fossil record and the physics of the impact intersect in the most extraordinary way. The Tanis Site. If you are not familiar with Tanis, stop whatever you are doing and appreciate this. It is one of the most scientifically significant fossil sites ever discovered. Located in the Hell Creek Formation of North Dakota, it was first described in detail in a paper published in the Proceedings of the National Academy of Sciences in 2019 by Robert De Palma and colleagues.
The site preserves, in a single geological layer less than 2 meters thick, the remains of an ecosystem that was killed within the first hour of the Chicxulub impact. Not the first year, not the first month, the first hour. How do we know? Because the mechanism that killed the animals at Tanis has been identified with extraordinary precision. The site preserves a deposit of what geologists call a seiche, a standing wave generated in a body of water by the seismic energy of the impact. The Chicxulub impact was not just an explosive event. It was also the largest earthquake in the history of the Earth, at least since the Hadean Eon. The seismic waves it generated propagated outward through the planet's crust at several kilometers per second, reaching North America within approximately 13 minutes. When those seismic waves reached the river systems of the Hell Creek floodplain, they set the water oscillating. The rivers sloshed back and forth in their channels, and in doing so, they deposited the material that preserved the Tanis site: fish, plant material, insects, small vertebrates, and, embedded within the deposit like a timestamp, glass spherules from the Chicxulub impact. Those spherules, microtectites, are found embedded in the gills of the fossilized paddlefish and sturgeon at Tanis. They were filtering them from the water as they breathed, which means they were alive when the spherules were falling, which means they died within the time frame of the spherule fall, which the physics of the impact and the trajectory calculations constrain to within the first hour after impact. This is paleontology as time travel, a single river deposit in North Dakota, precisely dated to within 60 minutes of the worst day in the history of complex life. What did the animals at Tanis experience? First, approximately 13 minutes after impact, the ground moved, not gently.
The seismic waves from Chicxulub, arriving in North Dakota, generated ground accelerations comparable to a very large earthquake. Estimates suggest the equivalent of a magnitude 10 or 11 seismic event, which is beyond anything in recorded human history. For comparison, the largest earthquake ever recorded by modern instruments was the 1960 Valdivia earthquake in Chile, which measured magnitude 9.5. The Chicxulub-generated seismic event arriving at Hell Creek was likely 10 to 30 times more energetic than that. The Edmontosaurus in the river would have felt the ground moving beneath them. The river itself would have begun oscillating, water sloshing back and forth in its channel as the seismic waves passed through. Trees would have been shaking. The birds, and there were birds in the late Cretaceous, genuine avian dinosaurs, descendants of theropods, would have taken flight. Every animal capable of movement would have been responding to ground motion unlike anything in the sensory experience of their species. But this was not the lethal event. This was the warning that the lethal event was coming. 25 minutes after impact. The sky is beginning to change, not dramatically, not yet, but to an observer looking upward from the Hell Creek floodplain, the first signs are appearing. The high cirrus clouds have taken on an unusual luminosity, not the normal brightness of sunlit ice crystals, something different. A faint but increasing glow from above, as the first wave of re-entering ejecta begins heating the upper atmosphere. The glass spherules are falling now. They have been falling for several minutes across the northern hemisphere, following their ballistic arcs back from the edge of space. They are too small to see individually, between 100 micrometers and a few millimeters in diameter, roughly the size of very fine sand grains. But they are falling in their trillions, and as they pass through the atmosphere, they are transferring energy to the air around them, raising temperatures at altitude. At Tanis, the river is already turbulent. The seiche generated by the seismic waves has turned the normally calm floodplain waterways into something dangerous and confused. Fish are being thrown against banks and sandbars. The paddlefish and sturgeon whose remains De Palma and his team would find 66 million years later are caught in this churning water, swept against debris, stunned. Some are already dying. Their gills continue filtering water, and the spherules falling into the river from above, even as they struggle. 35 minutes after impact, the thermal pulse is arriving. This is the moment that the physics calculations have been pointing to. The ejecta re-entry heating, the global oven effect described by Toon and colleagues, has reached a threshold where it is beginning to measurably increase surface temperatures across the northern hemisphere. The effect is not uniform. It depends on cloud cover, latitude, and the local density of falling debris. But in the Hell Creek region, the sky is clearing as the morning progresses, and the thermal pulse is arriving without significant attenuation. The temperature is rising. Not slowly the way a summer afternoon heats up, rapidly, uncomfortably. The air above the tree canopy is hotter than the air beneath it, which is itself hotter than it was 20 minutes ago. Animals are responding. The Edmontosaurus herd has left the river. They are moving into the denser forest, instinctively seeking shade, seeking cover. This is the behavior of animals experiencing heat stress, a response pattern documented across living taxa and entirely consistent with what the thermal physics of the impact predicts for this latitude. The Triceratops on the forest edge is standing still, head slightly low.
Its frill, richly vascularized, normally used for thermoregulation as well as display, is flushed with blood as its circulatory system attempts to shed excess heat. It is an extraordinarily efficient cooling mechanism under normal circumstances. But these circumstances are not normal. The sub-adult Tyrannosaurus has moved into deep forest cover. Its body temperature, already running warm, as we know from bone histology studies that confirm theropod dinosaurs had elevated metabolic rates, is rising faster than it can dissipate. It stands in the shadows, mouth slightly open, its respiratory system working. 45 minutes after impact. The sky is on fire. Not literally, not yet, not at this latitude. But the luminosity above the cloud layer has reached a level that is visible even in daylight. The horizon to the south and southwest, in the direction of the Yucatan, carries a glow that is wrong in every way that an animal's evolved senses can measure. It is the color of something impossible, a light that has no place in the vocabulary of any living nervous system on Earth. The temperature in the Hell Creek floodplain is now 10 to 15 degrees Celsius above the morning baseline. In the span of less than an hour, a warm spring morning has become something between an extreme heat event and a low-level thermal assault. Dry vegetation is beginning to desiccate at its surfaces. The leaf litter on the forest floor, normally moist with the humidity of the subtropical environment, is losing moisture rapidly. The resins in the conifer trees are responding to the heat, becoming more volatile, releasing compounds into the air that would be, to a human nose, the smell of a forest about to burn. And then, in certain locations, hilltops, exposed ridges, clearings where the thermal pulse can reach the ground without the attenuation of a forest canopy, it begins. Fire.
Not the single catastrophic wildfire of popular imagination, a wall of flame sweeping across the continent in a single afternoon. The reality, as modeled by researchers including those publishing in the Journal of the Geological Society, is more complex and ultimately more thorough. Fires begin in isolated locations where conditions are right, and they spread over hours and days and weeks, eventually burning across vast areas of the Northern Hemisphere. But in the first hour, in the Hell Creek floodplain, what is happening is the ignition of the first fires in a conflagration that will, over the coming weeks, consume enormous areas of Laramidia. The smoke from those first fires rises into an atmosphere already carrying dust and glass spherules from the impact. The column of smoke is black and dense against a sky that has already taken on a brownish, bruised quality as the ejected dust begins to diffuse across the upper atmosphere. 1 hour after impact, the animals at Tanis are dying. The river has partially receded, leaving fish stranded on mudflats and sandbars. The seiche has deposited a layer of sediment across the floodplain that is already beginning to entomb the dead and dying. The paddlefish lie gasping in the shallows. The sturgeon are still. On the bank, the bodies of small mammals, shrews, early multituberculates, the furtive, warm-blooded creatures of the undergrowth, are beginning to accumulate in the debris. Above them, in the warming air, the glass spherules continue to fall. And somewhere in the rock above the Yucatan Peninsula, the crater at Chicxulub is still settling. The temporary mountain of liquid rock at its center has long since collapsed. The mega-tsunami generated by the impact is already propagating outward across the Proto-Caribbean, across the Gulf of Mexico, carrying walls of water that will devastate coastal ecosystems thousands of kilometers from the impact site. The seismic waves are still moving through the planet's crust, traveling around the globe, arriving on the far side of the Earth within 20 minutes, registering in geological formations from what will become Europe to what will become China. The Cretaceous is not over yet. 90% of the animals that will die in this extinction event are still alive. The Tyrannosaurus in the Hell Creek forest is still alive. The Triceratops is still alive. The mosasaur in the western interior seaway is still alive. But the world they live in, the world of warm, stable climate, of continuous forests, of the rich and complex ecosystem that 66 million years of evolution had assembled, that world has already received a wound that nothing can heal. It does not know this yet. The fires are small. The sky is strange but still bright. The temperature is uncomfortable, but not yet lethal for a large-bodied animal in forest cover. For an Edmontosaurus standing in the shade of a conifer, pressing its bulk against the relative coolness of the deep forest, this is terrifying and incomprehensible. But it is survivable. For now. In 66 million years, a team of scientists will drill into the floor of the Gulf of Mexico and extract a core of rock that passes through the KPG boundary. They will find in that core layers that tell the story of what happened in the hours and days and months after this moment. They will find the ash, the spherules, the iridium, the evidence of wildfire in the form of charred plant material distributed globally, the evidence of ocean acidification, the evidence of a sky that went dark and stayed dark. They will read it all. But right now, in the Hell Creek floodplain, 1 hour after the largest impact in 66 million years, a subadult Tyrannosaurus rex is standing in the shadows of a conifer forest, and the world it was born into is still, just barely, intact. The next 23 hours will take everything. 2 hours after impact, the sun is still up. This is the detail that surprises most people when they encounter the serious scientific literature on the Chicxulub impact. Popular imagination tends to compress the extinction into a single apocalyptic moment. The rock hits, the world ends, darkness falls, everything dies. But the reality recorded in the geological evidence is at once more drawn out and more terrible than that. The sun did not vanish in the first hour. The sky did not go black immediately. For a significant portion of that first day, the animals of the Hell Creek Formation could still see, could still move, could still, in some fundamental biological sense, hope. What they could not do was escape what was coming. The sky above the Hell Creek floodplain is the color of a bruise, not the clean blue of the morning. The ejecta dust, the finest fraction of the material thrown up by the Chicxulub impact, particles measured in micrometers, has begun its global dispersal across the stratosphere. The stratosphere sits between approximately 12 and 50 kilometers above the surface, and material injected into it travels differently from material in the lower atmosphere. It is not rained out quickly. It is not swept away by weather systems. It circulates in the stratospheric winds, spreading horizontally across the entire planet, and it stays there for months, for years, for as long as the particles remain too fine to fall efficiently under gravity. The dust veil is not yet complete. It will not reach its maximum opacity for days, perhaps weeks, but it has already begun to scatter and absorb incoming solar radiation, and the effect on light quality at the surface is measurable. The light has lost its crispness. Shadows are softer than they should be for late morning. The sun itself, still visible, has taken on a quality that has no normal analog, a flat, white-yellow disk surrounded by a brownish halo that sits wrong in the sky, that communicates to every evolved visual system on the planet that something is not right. Animals read light. This is not a trivial point. Circadian rhythms, the biological clocks that govern sleep, feeding, hormone cycles, and dozens of other physiological processes, are calibrated to the quality and quantity of sunlight. Changes in light quality trigger responses at the neurological level. The birds in the Hell Creek forests, genuine avian theropods, small feathered animals whose descendants would survive this event and eventually fill the skies of our world, are behaving as though dusk is approaching. Some have stopped singing. Some are moving to their roost positions. Their internal light meters are telling them that afternoon is further along than it should be. The large dinosaurs cannot read this signal so finely, but they feel the heat, and they feel the absence of the breeze that normally moves through the floodplain in the morning hours. The air is strangely still. The thermal pulse from the ejecta reentry has disrupted the normal convective patterns that create wind, and the atmosphere over the Hell Creek region is sitting in an eerie calm that amplifies the heat rather than dispersing it. 3 hours after impact, the fires to the south and southwest are visible from high ground, not as a wall of flame, not yet, as columns of smoke rising dark and vertical in the still air, climbing into the haze layer and spreading out at altitude into a widening canopy of gray-brown that adds to the already compromised quality of the light. From the perspective of an animal on the Hell Creek floodplain, this is simply a darkening in the southern sky. But the smell is already present, carried northward even without strong wind by the simple diffusion of a vast plume of combustion products working its way through the atmosphere. The smell of burning forest is one of the most ancient and powerful alarm signals in the behavioral repertoire of terrestrial vertebrates. It has been eliciting flight responses since long before the Cretaceous, and the animals of the Hell Creek ecosystem are responding to it now, even at this distance, even at this dilution. Not with the precise directional response of a modern mammal processing olfactory information through a highly developed cerebral cortex, but with a generalized agitation, a heightened readiness, a restlessness that is moving through the herds and flocks and solitary hunters of the floodplain like a current through water. The Edmontosaurus herd is moving north, not in a panic. There is no predator triggering a flight response, no immediate physical threat driving them. They are simply moving the way large herbivores move when the environment becomes uncomfortable, following the gradient from less comfort to more, driven by the same navigational instincts that guide wildebeest migrations across the Serengeti today. But there is no more comfortable place to go. The discomfort is not local. It is not a patch of bad weather or an isolated fire that can be walked away from. It is the entire southern and western sky. It is the temperature of the air itself. It is the quality of the light. The Edmontosaurus herd is trying to migrate away from a catastrophe that spans a hemisphere. In the rivers, something else is happening. The mega tsunami generated by the Chicxulub impact, the wall of water displaced by the entry of 12 to 15 cubic kilometers of rock into the shallow waters of the Proto-Caribbean, has been traveling outward from the impact site at speeds consistent with deep water wave propagation, several hundred meters per second. At this speed, the wave front has already crossed much of the Gulf of Mexico. It is approaching the shallow coastal regions of what will become Texas, Louisiana, and Mississippi. The low-lying coastal plains of late Cretaceous Laramidia, where the western interior seaway meets the land. The wave, arriving in shallow water, is undergoing the transformation that all tsunamis undergo as they shoal. It is slowing down, compressing, and increasing dramatically in height. What was a fast-moving deep-water pulse, perhaps tens of meters high in the open ocean, is now becoming a wall of water, potentially hundreds of meters high, as it meets the continental shelf. Research published in the journal Earth Science Reviews, modeling the Chicxulub tsunami in detail, suggests that the wave energy was sufficient to inundate coastal areas across much of the Gulf of Mexico margin and beyond, with run-up potentially reaching hundreds of kilometers inland across the flat, low-lying coastal plains. The geological evidence for this is preserved in formations across Texas and Alabama. The Brazos River section in Texas, for example, contains a distinctive bed of coarse-grained sediment at the KPG boundary that researchers have interpreted as a tsunami deposit, with the kind of chaotic, poorly sorted material that high-energy wave inundation produces. In the shallow waters of the western interior seaway itself, the seismic waves and pressure pulses from the impact have already disrupted the surface. The mosasaur that was hunting this morning is deep now, driven down by the turbulence at the surface. But deep water offers no safety from what is coming. The seaway, relatively shallow at its maximum depth, is transmitting the seismic energy efficiently from bed to surface, and the entire water column is disturbed in a way that has no precedent in the experience of any animal alive in it. 4 hours after impact. Let us leave the Hell Creek floodplain for a moment and go to the other side of the world. Because the Chicxulub impact was not a regional event, it was not even a continental event. It was a planetary event. And understanding its full scope requires us to step back from the immediate devastation of North America and acknowledge that at this exact moment, 4 hours after impact, the effects are being felt on every landmass, in every ocean, at every latitude. In what will become Morocco, on the Atlantic coast of northern Africa, it is late afternoon. The sun is several hours further along in its arc than it is in North America. The marine ecosystem of the Moroccan phosphate deposits, a rich, diverse assemblage of sharks, bony fish, sea turtles, and mosasaurs, preserved in extraordinary detail in the Oulad Abdoun Basin, is being disrupted by seismic waves arriving from across the Atlantic. The fish in the surface waters are agitated. Some species are exhibiting the kind of mass schooling behavior associated with the detection of seismic ground motion, a response documented in living fish species that seems to be an ancient, deeply conserved reaction to disturbance in the substrate. But the sky here is still relatively clear. The ejecta dust has not yet reached Africa in significant concentration. To an animal on the Moroccan coast, 4 hours after impact, the world looks almost normal. Almost. The quality of the light is very slightly off. There is an unnatural calm in the atmosphere. And in the east, as the sun moves toward the horizon, the sunset will be unlike any sunset that has come before. The thin veil of stratospheric dust, already present in the upper atmosphere, will scatter the light into colors and intensities that have no precedent. It will be, by any aesthetic measure, extraordinarily beautiful. It will be the last sunset of its kind. In what will become Antarctica, still forested in the late Cretaceous, still warm enough to sustain dinosaur faunas, currently experiencing a late spring evening as the long austral days of the southern summer approach, the seismic waves have arrived and passed. The ground moved, animals responded, and then the movement stopped and the world seemed to return to normal. But the ejecta is already in the stratosphere above the South Pole. It arrived there carried by high-altitude winds. It is thin, far thinner than it will eventually become, but it is present. The global dispersal of the finest impact material is faster than almost anyone would intuitively expect. The stratospheric circulation carries material around the planet on timescales of days to weeks, not months. The sky above Antarctica on the evening of Impact Day is already, very subtly, not the sky it was that morning. 5 hours after impact, back in Hell Creek, the temperature has peaked. This is a critical point in the timeline, and one that the scientific literature handles with some complexity. The thermal pulse from re-entering ejecta was intense but relatively brief, a matter of hours, not days. After the peak of re-entry heating, as the flux of returning material decreases, the direct thermal assault on the surface begins to ease. Temperatures that had risen by perhaps 10 to 20 degrees Celsius above baseline in exposed areas begin very slowly to drop back. But they do not drop back to normal, because the atmosphere is now loaded with material that is doing something different, not heating the surface by re-entry, but beginning to block the sunlight that normally warms it. The transition is from a world being briefly overheated to a world being progressively starved of light and warmth. And that transition from heat pulse to cold darkness is the mechanism that will kill the majority of the species that this day destroy. The large dinosaurs that survived the first hours by sheltering in forest, by moving to shade, by pressing their bulk against the thermal inertia of their own bodies, these animals are now facing a different and more insidious threat. Not fire, not heat. The slow grinding withdrawal of the energy that powers every food web on Earth. But this is still hours, days away from becoming the primary killer. Right now, in the late afternoon of Impact Day, the most immediate threats for animals in the Hell Creek region are fire, heat stress, and the psychological, if we can use that word loosely, disorientation of an environment that has become utterly alien. 6 hours after impact. The fires are closer. The wind has returned, and with its return has come a new danger. As the thermal disruption of the atmosphere begins to generate pressure differentials, the air that was eerily still this morning is now moving again, but not in the gentle, reliable patterns of a normal afternoon. The air is moving in confused, variable directions, the atmosphere attempting to equilibrate the temperature gradients generated by the impact heating, the fires, the disruption of the normal convective cycles. And the wind is feeding the fires. A wildfire, once established, creates its own weather system. It generates strong updrafts as superheated air rises from the burning surface, drawing in fresh oxygen from the surrounding area at ground level. This inflow of fresh air accelerates the burning. The fire grows. It generates stronger updrafts. More air is drawn in. The cycle is self-reinforcing, and in a landscape of dry vegetation already stressed by hours of abnormal heat and desiccation, fires can spread with terrifying speed. The conifer forests of the Hell Creek region, with their resin-rich wood and their deep accumulations of dry needle litter, are particularly combustible. Research into the KPG boundary layer has consistently found elevated concentrations of polycyclic aromatic hydrocarbons, chemical compounds produced by the combustion of organic matter, in sediments of this age from sites around the world. This is one of the chemical signatures of global wildfire in the geological record. The fires that began in the first hour are spreading, and the atmospheric record of that spreading is preserved in the rock. 7 hours after impact. In the interior of Laramidia, far from the fires, far from the coast, the late afternoon light is extraordinary in its wrongness. The sky is no longer the color of any sky these animals have ever seen, or that any living thing on Earth has seen in millions of years. The dust and aerosol loading in the upper atmosphere has reached the point where the solar disk, still above the horizon, is no longer the bright yellow-white of a normal afternoon sun. It is orange, then red. Then, as more material enters the upper atmosphere with each passing hour, it becomes something dimmer and more diffuse, a smear of red-orange light that gives the landscape a quality that has no name because no language has ever needed to describe it. The shadows have gone soft. In a normal late afternoon, shadows are sharp, clear-edged, dark. Now, with the sunlight scattered by billions of tons of airborne particles, the light is coming from every direction at once, diffused across the entire sky. There are no shadows, just a dim red-orange glow that illuminates everything equally and inadequately. The Triceratops that was browsing at the forest edge this morning is standing still in the middle of a clearing, and it is doing something that would be remarkable to observe if any observer existed. It is looking at the sky. Not because it understands what the sky means, not because it is capable of any cognitive framework that would allow it to comprehend what has happened or what is coming, but because every evolved sensory system it possesses is screaming that something is profoundly wrong, And in the absence of a specific threat to respond to, no predator, no rival, no flood, it is standing still, processing a world that its nervous system has no template for. The frill on its skull, normally bright with vascular color, is pale. The animal is not in a display state. It is in a state that has no good analogy in its behavioral repertoire. It is experiencing something that its species has never experienced before in an unbroken lineage stretching back millions of years. The last new thing. 8 hours after impact. Night is coming, and this night will be different from every night that has come before it, because the darkness will not be the normal darkness of an Earth without artificial light, a darkness punctuated by stars, relieved by the moon, broken by the first gray light of dawn after a few hours. This darkness will be deeper. The stratospheric dust is already thick enough to obscure a significant fraction of starlight. The moon, if it is above the horizon, is a dim smear rather than the bright disk it has been for 4 billion years. And when dawn comes, if dawn can be said to come at all in the days and weeks after the impact, it will not be the dawn that ended the previous night. It will be something dimmer, colder, and more final. But the animals do not know this yet. For them, this is simply night. Strange, wrong in ways they cannot articulate, but night. The Edmontosaurus settle. The small mammals emerge from their burrows, as they always do at darkness, and begin foraging. The Tyrannosaurus, a nocturnal and crepuscular hunter in part, moves through the forest. Its extraordinary sense of smell is still fully functional. The dust in the air carries chemical information from the burning regions to the south, but here, in the northern reaches of the Hell Creek floodplain, there is still prey. Still the scent of living animals. The night proceeds, and somewhere in the stratosphere, 30 kilometers above the Hell Creek floodplain, the dust is still spreading, still thickening, still beginning the slow, inexorable process of blocking out the sun. The fires burn through the night to the south, their light, flickering orange reflected off the undersides of smoke clouds, provides the only illumination of a sky that has forgotten how to be ordinary. The dinosaurs of Hell Creek have survived the first 8 hours. They will survive the night. But the enemy that will kill them is not the fire on the horizon, or the heat of the afternoon, or the walls of water crashing over distant coasts. It is the darkness gathering overhead, grain by grain, particle by particle, in the cold and silent stratosphere. It is the death of the light, and it has only just begun. 24 hours after impact, dawn comes, or rather, something comes that occupies the position in time where dawn should be. The Earth has completed its rotation. The geometry is correct. The sun is above the horizon of the Hell Creek floodplain. Photons are leaving the solar surface, crossing the 150 million kilometers of vacuum between the sun and the Earth, entering the upper atmosphere exactly as they have done every morning for 4.5 billion years. But they do not arrive at the surface. Not most of them. In the 24 hours since the Chicxulub impact, the stratospheric loading of fine particulate matter has reached a level that researchers modeling the impact winter effect have described as without precedent in the Cenozoic era. The dust is not alone up there. It is accompanied by sulfur dioxide, enormous quantities of it, released by the vaporization of the sulfur-rich evaporite deposits of the Yucatan Carbonate platform. The Chicxulub impactor hit what was, from the perspective of maximum atmospheric damage, almost the worst possible target geology on Earth. The limestone and evaporite rocks of the Yucatan, contained sulfur in concentrations that, when vaporized and injected into the stratosphere, produced sulfate aerosols, tiny droplets of sulfuric acid that are even more effective at blocking sunlight than dust particles. Research published in the journal Geophysical Research Letters has estimated that the Chicxulub impact injected somewhere between 300 and 500 gigatons of sulfur dioxide into the atmosphere. For comparison, the 1991 eruption of Mount Pinatubo in the Philippines, the largest volcanic eruption of the 20th century, injected approximately 20 megatons of sulfur dioxide and caused a global temperature drop of about half a degree Celsius, lasting roughly 2 years. Chicxulub released somewhere between 15,000 and 25,000 times as much sulfur dioxide as Pinatubo. The climate consequences of this were not subtle. But on this first dawn, 24 hours after impact, what matters most to the animals standing in the Hell Creek floodplain is not the chemistry happening 30 kilometers above their heads. What matters is what that chemistry produces at ground level. The light is wrong. The sun, which should be rising brilliant and gold above the eastern horizon, is a dim red disk barely distinguishable from the surrounding sky. The quality of illumination reaching the surface is comparable not to dawn, but to a heavily overcast winter afternoon, dim, diffuse, directionless. The shadows that should be stretching long and sharp across the floodplain in the low angle of morning light simply do not exist. The world is lit by a flat, reddish-gray glow that drains color from everything it touches. The temperature has dropped overnight. Not catastrophically. Not yet. The thermal mass of the oceans and the deep soil buffer the surface temperature against rapid change. A single day is not enough to override billions of tons of stored heat. But the overnight low was measurably cooler than it should have been for a late spring night at this latitude. The morning air that should carry the warming promise of a subtropical dawn feels instead like early autumn. Not the chill of a killing frost, not yet, but the first whisper of a cold that will deepen over the coming weeks and months into something the Hell Creek ecosystem is entirely unprepared for. The small mammals in their burrows feel it first. They feel it because small-bodied animals lose heat rapidly and require frequent feeding to maintain their metabolic rate. The drop in overnight temperature has cost them more energy than a normal night. They emerge from their burrows into the dim morning already slightly depleted, already needing food more urgently than usual. They begin foraging in the half-light, their whiskers working through leaf litter, their sensitive noses reading the chemical landscape of the forest floor. What they find is not encouraging. The forest floor is changed. The layer of leaf litter, normally a rich ecosystem in itself, supporting insects, worms, fungi, and the bacteria that break down organic matter into the nutrients that feed the plants above, has been partially destroyed by the heat of the previous day. The surface layer is desiccated, in places scorched. The insects that live in it, the beetles, the ants, the termites, the countless small arthropods that form the base of the forest floor food web, have been killed or driven deeper into the soil. The forest floor, normally teeming with life at the millimeter scale, is quieter than it has ever been. But the mammals find enough. This first morning, the ecological disruption is severe, but not yet total. There are still insects. There are still seeds and berries and fungal material. The small, warm-blooded creatures that will eventually inherit the earth are hungry, but not starving. Not yet. Above them, the forest is still. The birds, the true birds, the avian dinosaurs, the feathered descendants of theropods that had been diversifying since the Jurassic, are not singing. This is significant. Birdsong is not merely aesthetic. It is functional. It communicates territory, attracts mates, maintains flock cohesion. The dawn chorus, which in a healthy temperate or subtropical ecosystem is one of the most complex and information-rich acoustic events in nature, is absent this morning. The birds are present. Many of them survived the first day in the canopy, sheltered from the worst of the thermal pulse. But they are silent. Their light-sensitive biological clocks, calibrated to a dawn that should be bright and warming, have received instead a signal that registers somewhere between deep overcast and the onset of dusk. Their hormonal systems are responding accordingly. The neurological trigger for dawn chorus behavior, a surge in luteinizing hormone driven by light intensity crossing a threshold, has not fired. The forest is wrong in a way that operates below the threshold of conscious recognition, but above the threshold of biological response. Every living thing in it knows, at the level of cellular chemistry, that something has changed. 30 hours after impact. The Triceratops that survived the first day is feeding. This is the thing to hold on to, because it is the thing that makes the extinction simultaneously comprehensible and heartbreaking. The large dinosaurs did not die on impact day. They were not killed by the blast wave or the heat pulse or the fires in the first hours, unless they were unlucky enough to be in the wrong place. They survived. They went to sleep on the night of impact day, and they woke up on the morning after. And they were hungry, and so they ate. The Triceratops is browsing on low-growing plants at the forest edge, as it has done every morning of its life. Its dental batteries, the complex, grinding teeth of a large ceratopsian, are processing vegetation efficiently. Its digestive system is functioning. Its muscles are working. Its heart is beating. It is alive, and for this moment, it is fine. But what it is eating has begun to change in ways that are invisible at this scale of observation. The plants it is consuming, the flowering angiosperms and ferns that dominate the low-growing vegetation of the Hell Creek floodplain, are already under stress. They have been under stress since yesterday morning's heat pulse. The photosynthetic machinery in their leaves, the chloroplasts, the reaction centers, the enzyme complexes that capture sunlight and convert it into chemical energy, is sensitive to both extreme heat and to reduced light intensity. After 24 hours of disrupted light and yesterday's thermal stress, the photosynthetic rate of the plants in the Hell Creek ecosystem has dropped measurably. Not catastrophically. The plants are still alive, still producing sugars, still converting sunlight to biomass, but the efficiency is down. The rate of new growth has slowed. And this matters because the entire food web of the Hell Creek ecosystem is built on a foundation of plant productivity. Every hadrosaur, every ceratopsian, every ankylosaur, every small herbivore, all of them are ultimately powered by the chemical energy that plants extract from sunlight. Reduce the light, reduce the plant growth. Reduce the plant growth, reduce the food available to the herbivores. Reduce the herbivore populations, reduce the food available to the predators. The dominoes are not falling yet, but they have been tipped. 40 hours after impact. The sky is darker than yesterday. This is the trajectory, and it does not reverse. Each passing day brings a slightly thicker stratospheric veil as the high-altitude winds continue to circulate and distribute the impact ejecta across the globe, as the sulfate aerosols continue to form from the injected sulfur dioxide, as fresh material continues to rise from the ongoing wildfires burning across vast areas of the Northern Hemisphere. Computer climate models of the post-Chicxulub environment including landmark simulations published by researchers including Joanna Morgan at Imperial College London and colleagues using the three-dimensional climate models originally developed for nuclear winter scenarios, project that within the first 2 weeks after impact, surface light levels across large areas of the planet will have dropped to below 1% of normal. Below 1%. In practical terms, this means that the amount of sunlight reaching the surface is less than what you would receive on a heavily overcast night with a full moon. Plants cannot photosynthesize in those conditions. At below 1% of full sunlight, the photosynthetic rate of most plant species drops to effectively 0. They can survive for a while on stored chemical energy, sugars and starches accumulated in roots and stems and seeds. Some species, particularly those with deep root systems and substantial energy reserves, can persist in this dormant state for weeks or even months. But they cannot grow. They cannot produce new leaves or seeds. They are drawing down their reserves, and when those reserves are exhausted, they will die. The ecological cascade this sets in motion is one of the most thoroughly documented aspects of the KPG extinction, and it is visible in the fossil record with remarkable clarity. Paleobotanical studies of KPG boundary sections, examining pollen, spores, and plant macrofossils in the rock layers immediately above and below the boundary, show a dramatic and near instantaneous shift in vegetation composition. Below the boundary, rich, diverse, angiosperm-dominated flora, reflecting the complex forests and meadows of the late Cretaceous. Above the boundary, a sudden spike in fern spores. This is called the fern spike, and it is one of the most haunting features of the KPG record. Ferns are ecological opportunists. They are among the first plants to colonize devastated landscapes because their spores are small and light and travel far, and because they can grow from underground rhizomes that survive conditions lethal to the above-ground parts of the plant. After every major volcanic eruption, after every forest fire, after every catastrophic disturbance, ferns come back first. They are the pioneers of ruined landscapes. The fern spike at the KPG boundary tells us that after the impact, the complex vegetation of the late Cretaceous, the forests of conifers and flowering trees, the meadows of ground-covering angiosperms, the dense riparian vegetation of river systems, was largely destroyed, and that what replaced it in the short term was a world dominated by ferns. A gray-green, low-growing, species-poor carpet of vegetation spreading across a landscape that had once been a forest. But that fern world is still weeks away. On this first morning after impact, the forests are still standing. The trees are still alive. The Triceratops is still finding food. 48 hours after impact. 2 days. The Tyrannosaurus in the northern reaches of the Hell Creek floodplain has not eaten since before the impact. This is within its normal tolerance. Tyrannosaurus, like large living predators such as Komodo dragons and large crocodilians, was almost certainly capable of surviving extended periods without food. Its large body mass, even for a subadult, provided thermal and metabolic buffering. It could go days, possibly weeks, without a significant meal. Research into bone isotope chemistry and growth rates suggests that T-Rex was not a constant hunter, but a periodic feeder, making large kills and then subsisting on the energy from those kills for extended periods. But it is hungry, and the prey in the floodplain is behaving differently. The Edmontosaurus herd has fragmented. This is abnormal. Hadrosaur herding behavior, well documented from trackway evidence across numerous Hell Creek Formation sites, was almost certainly a predator avoidance strategy, a collective defense mechanism where many eyes and ears improved the group's ability to detect threats. The fragmentation of the herd in the 36 hours since the impact suggests that the ecological disruption has overridden the normal social bonding mechanisms. Animals are separating, following individual gradients of hunger and stress, moving away from the smoke and heat to the south and west without the cohesion that normally keeps the group together. Isolated hadrosaurs are easier targets. The Tyrannosaurus finds one. An elderly Edmontosaurus, a large female, perhaps 12 years old, moving slowly through a burnt-over area where the fires of yesterday have reduced the ground cover to black stubble and ash. She is disoriented. The familiar landmarks of the floodplain, the stands of trees, the river meanders she has navigated for years, are changed, some destroyed, all overlaid with the gray-brown haze that makes distances and details uncertain. What follows is the last act of the most ancient drama in the Hell Creek ecosystem. Predator and prey in a world that is already ending. The Tyrannosaurus does not know that this kill is different from every kill that came before it. It does not know that the ecological web that makes this moment possible, the web of plants and herbivores and predators that has been functioning in this floodplain for millions of years, is already beginning to unravel above their heads, in the stratosphere where the light is dying. It knows only that it is hungry, and that there is prey. The kill is made. The Tyrannosaurus feeds. And this, perhaps more than any other single image from that first day and night, captures the true nature of what the extinction event was. It was not a wall of fire. It was not an instant death. It was a slow and terrible unwinding of a world that did not know it was ending, populated by animals that continued to do what they had always done, right up until the moment they could not. The tyrannosaur feeds on the carcass in the gray morning light, surrounded by the smell of ash and the strange, flat illumination of a sky that has forgotten how to be bright. Above it, the sun is up, but it is barely there. 50 hours after impact, the temperature has dropped another degree. In the oceans, something equally profound is beginning. The surface waters of the world's seas, the photic zone, the thin upper layer where sunlight penetrates and where the vast majority of marine photosynthesis takes place, are receiving less solar energy with each passing day. The phytoplankton, the microscopic algae and cyanobacteria that form the foundation of virtually every marine food web on Earth, are already showing reduced photosynthetic rates. This matters enormously, because the marine extinction component of the KPG event is often overshadowed by the dramatic terrestrial story, but was equally devastating. The loss of phytoplankton from the marine food web cascades upward with the same inexorable logic as the loss of plants from the terrestrial food web. Less phytoplankton means less zooplankton. Less zooplankton means less food for small fish. Less small fish means less food for large fish and marine reptiles. And simultaneously, the ocean surface is acidifying. The carbon dioxide released by the impact and the wildfires is dissolving in the surface water, forming carbonic acid, lowering the pH, beginning to dissolve the calcium carbonate shells of ammonites, mollusks, and the calcareous plankton that form the base of calcified marine food webs. The ammonites, those extraordinary spiral-shelled cephalopods that had been diversifying and thriving in the world's oceans for 330 million years, surviving every previous mass extinction, filling every marine niche from shallow reef to open ocean, are about to face conditions that their shells, however beautiful, were never built to withstand. They will not survive this one. The mosasaur in the western interior seaway is still alive on the morning of this second day. It is still hunting. The The seaway is disturbed. The water is turbid with stirred sediment. The surface is choppy with confused currents generated by the seismic disruption. But there are still fish. There are still ammonites. The mosasaur's food supply has not yet collapsed, but the light at the surface is wrong. Even for an animal that hunts by vision in 3 dimensions, the quality of the light matters. The reduction in solar irradiance that has already occurred is not yet severe enough to make hunting impossible, but it is measurable. The visibility in the upper water column is reduced. The brightness that normally guides the mosasaur's binocular vision as it tracks fast-moving prey through the water has been diminished. It is a small thing today, but the direction is established. 66 million years later, in the chalk formations of Kansas, the Niobrara chalk deposited in the floor of the western interior seaway, paleontologists will find the last mosasaurs. Their bones are abundant below the KPG boundary. Above it, they are absent, not reduced, not diminished, absent. The line in the rock is absolute. But on this second morning, the mosasaur does not know it is the last of anything. It dives. The water closes above it. Its powerful tail drives it deeper into the green-blue murk of the seaway, hunting with the focused, evolutionary precision of 30 million years of marine adaptation. Above it, unnoticed, the sky is getting darker, and in the Hell Creek floodplain, the Triceratops is still browsing, and the Tyrannosaur is still feeding, and the small mammals are still in their burrows, and the dim red sun is tracing its arc across a sky that grows a little less transparent with each revolution of the Earth. The last day of the dinosaurs was not one day. It was every day that came after, each one a little darker, a little colder, a little hungrier. Each one containing animals that were doing what they had always done in a world that was quietly, systematically, irreversibly withdrawing the conditions that made their lives possible. The count is not hours now. It is weeks, months, years. And the darkness is only deepening. 1 week after impact, the sun is a rumor, not gone, not invisible, but reduced to something so attenuated, so drained of its normal authority, that the word sunlight no longer quite applies to what is reaching the surface of the Earth. It arrives as a dim, brownish-gray luminosity, enough to tell the difference between day and night, barely enough to cast a shadow, nowhere near enough to warm the ground or drive the chemistry of photosynthesis at meaningful rates. The average surface temperature across the northern hemisphere has dropped by somewhere between 8 and 15 degrees Celsius from the pre-impact baseline.
Climate modeling studies, including work published by researchers at the Potsdam Institute for Climate Impact Research, and simulations run using the CESM climate model by teams at the National Center for Atmospheric Research, project that within the first month after the Chicxulub impact, surface cooling in continental interiors could reach 20 degrees Celsius or more below normal seasonal temperatures. In the Hell Creek region, where late spring temperatures should be warm and humid, the air now feels like late autumn. Not freezing, not yet, but heading there. The rain is wrong too. It is raining across much of Laramidia, but the rain is not the warm, life-giving subtropical rain of the normal late Cretaceous spring. It is cold, and it is acid. The sulfur dioxide injected into the stratosphere by the impact has been converting to sulfate aerosols, and those aerosols are now beginning to wash out of the atmosphere as the aerosol particles grow large enough to fall under gravity. They dissolve into the rainwater as they fall, producing a dilute but measurable sulfuric acid precipitation, acid rain on a planetary scale over a period of months. The acid rain does not burn skin or melt bones. It is not concentrated enough for that. But it is sufficiently acidic. Research suggests pH values potentially dropping to 3 or 4 in areas of heaviest fallout, comparable to vinegar, to damage the waxy cuticle layer on leaves, to kill mosses and lichens, to acidify the upper layers of soil, to leach minerals from root zones, and to lower the pH of shallow freshwater bodies to levels that kill sensitive aquatic organisms. The frogs are dying. This seems like a small thing against the backdrop of planetary catastrophe, but it is not. Amphibians are exquisitely sensitive indicators of water chemistry.
Their permeable skin means they absorb what is in the water around them, and their eggs, gelatinous masses deposited in shallow freshwater, are unprotected against pH changes. The acid rain is killing the breeding populations of the late Cretaceous amphibians that lived in the river systems of the Hell Creek floodplain, and in doing so, it is removing a significant component of the food web that supports small predators. The snakes, the small crocodilians, the furtive insectivorous mammals that supplement their diet with amphibian eggs and juveniles. The cascade is accelerating. 2 weeks after impact. Stand in the Hell Creek floodplain now, and the world you encounter is almost unrecognizable as the same place that existed 2 weeks ago. The forest is still standing, the trees are still there, the conifers, the tree ferns, the early deciduous angiosperms. Their trunks and branches are intact. From a distance, the forest looks like a forest. But look more closely, and something is deeply, fundamentally wrong. The leaves are still. Not in the way leaves are still on a windless day, that quality of suspended anticipation before the breeze returns. Still in a different way, a finalized way. The broad leaves of the flowering trees are yellowing at their edges, the cells in them dying as the energy deficit from 3 weeks of inadequate sunlight depletes their reserves. The conifer needles are losing their dark green color, fading toward a dull gray-green that has no vitality in it. The forest is dying from the top down. The canopy, the layer of vegetation that normally intercepts the most light and is therefore the most productive, is suffering the most. Below the canopy, where shade was always the normal condition, the shade-adapted understory plants are holding on slightly better. Their physiology is calibrated for low light levels, but even they are approaching the limits of what their evolutionary heritage has prepared them for. The light levels now reaching the forest floor are below what even the most shade-tolerant species can sustain indefinitely. The insect populations have crashed. This is perhaps the most catastrophic single development for the long-term prospects of the Hell Creek ecosystem, because insects are not merely a food source. They are the infrastructure of the terrestrial food web. They pollinate the flowering plants. They break down dead organic matter. They are the primary food source for dozens of vertebrate species. They regulate plant populations through herbivory. They are, in the mathematical language of ecology, a keystone functional group. Remove them, and the architecture of the entire system begins to fail. The insect crash is driven by multiple simultaneous factors. The loss of plant productivity has cut off the food supply of herbivorous insects. The acid rain has destroyed many aquatic insect breeding grounds. The cold, still not lethal to large endothermic animals, but absolutely lethal to the ectothermic insects that depend on external warmth to complete their life cycles, has killed enormous numbers of adult insects and prevented the development of eggs and larvae. The darkness has disrupted the photoperiod cues that many insects rely on to time their emergence, their mating, their migration. The butterflies and moths, the Lepidoptera, already present in the late Cretaceous in early forms, do not emerge. Their caterpillars, dependent on specific host plants that are dying, are not completing their development. Their eggs, laid on plants that no longer have functioning leaves, are simply failing. The bees, early forms of which were already present and already performing pollination services for the angiosperms that had co-evolved with them, are not flying. The temperature is too low. The flowers are not opening properly in the reduced light. The colony structures, dependent on a continuous supply of nectar and pollen, are collapsing. The silence in the forest. The absence of insect sound that in a healthy late Cretaceous ecosystem would be a continuous, complex, layered acoustic texture is one of the most telling indicators of how completely the lower trophic levels of the food web have been disrupted. 3 weeks after impact, the Triceratops is thinner, not dramatically, not the visible skeletal thinness of an animal in the final stages of starvation, but the fat reserves that it accumulated through the productive late Cretaceous spring are being drawn down. Its body is making physiological decisions, reducing metabolic rate, mobilizing stored energy, directing resources away from non-essential systems toward the maintenance of core functions. These are the same decisions that every large vertebrate makes when food becomes scarce, and they can sustain life for weeks, sometimes months, in an animal of this body mass. But the vegetation the Triceratops depends on is not recovering. It is declining. The low-growing angiosperms that formed its primary diet, the plants whose tooth-wear isotope signatures paleontologists have read in ceratopsian dental enamel, are the plants most vulnerable to the combination of cold, darkness, and acid rain. They are the plants with the least energy storage in roots and rhizomes, the plants most dependent on continuous photosynthesis to sustain their above-ground biomass. They are dying faster than the Triceratops. The Tyrannosaurus, paradoxically, is in slightly better condition. Large predators are buffered against short-term prey scarcity by their ability to go extended periods without food and by their ability to scavenge. A Tyrannosaurus that makes a kill can sustain itself on that carcass for days. And in a landscape of increasing herbivore mortality, animals dying from cold, from starvation, from the accumulated stress of 3 weeks of environmental catastrophe, there are bodies. The smell of death is present in the air of the Hell Creek floodplain, carried by the cold wind, and the Tyrannosaurus is following it. But even for the apex predator, the trajectory is clear. Fewer herbivores means fewer prey animals, means fewer kills, means fewer calories. The apex predator is the last link in a chain that is shortening from the bottom up. And when the chain becomes short enough, the last link falls too. 1 month after impact. Snow. In the Hell Creek region, a landscape that at this latitude and in this climate had not seen snow in millions of years, possibly in tens of millions of years, it is snowing. The flakes are small and dry, driven by a wind out of the north that carries a temperature that has no precedent in the recent evolutionary history of anything alive in this ecosystem. Not a killing blizzard, not a dramatic cinematic snowstorm. A thin, persistent gray snow falling on a landscape of dying trees and yellowed, flattened vegetation and cold, dark rivers, and landing on the backs of animals that have no fur, no behavioral adaptation, no physiological preparation for this cold. The cold is not killing the large dinosaurs directly. The large dinosaurs, hadrosaurs, ceratopsians, ankylosaurs, tyrannosaurs, had elevated metabolic rates, as confirmed by bone histology studies examining growth rates and vascular patterns in dinosaur long bones, published by researchers including Gregory Erickson at Florida State University and Robin Reed at Queen's University, Belfast. They were not cold-blooded in the old, slow reptilian sense. Their metabolisms were running, generating heat. A large Edmontosaurus with its enormous body mass and elevated metabolic rate was not freezing to death in a light snowfall. It was starving to death in a landscape where the food had gone. This is the critical distinction, and it is the one that the fossil record encodes with brutal clarity. The KPG extinction was not primarily a death by fire event.
It was not primarily a death by cold event. It was a death by darkness event. A collapse of photosynthesis that propagated up through food webs with a logic as relentless and impersonal as mathematics. The pattern of survival at the KPG boundary reflects this with striking precision. Who survived? Small animals, birds and mammals, survived at far higher rates than large ones, not because they were smarter or more evolved, because they needed less food. A small mammal weighing 30 grams can sustain itself on a diet of seeds, fungus, and insect larvae. Food sources that remained available even in the post-impact environment, because seeds store energy chemically without requiring sunlight, and because fungi, which decompose dead organic matter rather than photosynthesizing, actually thrived in the post-impact world of dying vegetation, doing extraordinarily well in a landscape suddenly rich in dead and dying plant material. Freshwater animals survived at remarkably high rates. Freshwater ecosystems are fueled not primarily by in situ photosynthesis, but by organic matter washing in from the surrounding land, dead leaves, woody debris, the bodies of terrestrial organisms. In the post-impact landscape, as the dying forests shed their leaves and as terrestrial animal carcasses accumulated near waterways, the immediate food supply in freshwater systems was paradoxically enriched rather than depleted. The turtles, the crocodilians, the freshwater fish, they survived the initial catastrophe at rates that stand in sharp contrast to the near-total extinction of their terrestrial counterparts. The crocodilians deserve a specific moment of attention because their survival tells us something important about what the extinction selected for and against. Crocodilians in the late Cretaceous were diverse and widespread, occupying aquatic niches from freshwater rivers to coastal marine environments. They were large. Some species approached 10 meters in length. They were ectothermic, meaning they did not need to burn calories to maintain body temperature. They could go without food for extraordinarily long periods. Modern crocodilians have been documented surviving more than a year without feeding, under controlled conditions. They could eat almost anything: carrion, fish, invertebrates, terrestrial animals that came to the water to drink. Every one of those characteristics is a survival advantage in a post-impact world. They survive. They survive almost entirely intact as a group, carrying their ancient lineage across the boundary and into the Paleogene, while the dinosaurs they shared the rivers and swamps with are eliminated almost completely. Across the boundary and into survival also go the turtles. Turtles, armored, slow-metabolismed, omnivorous, capable of surviving long periods without food, capable of burrowing into mud and entering metabolic dormancy, are extraordinarily well suited to exactly the conditions the impact creates. They lose species, they lose diversity, but the group survives, and the turtles alive in the world today, the leatherbacks, the sea turtles, the freshwater terrapins, the tortoises, are the direct descendants of animals that lived through the worst day in the history of complex life. 6 weeks after impact, the Edmontosaurus herd, what remains of it,
is barely recognizable as the group of animals that was feeding at the river's edge on the morning of the impact. There were perhaps 30 individuals in the core group on that last morning. Now, there are 11. The others have died, some to the cold, some to starvation, some to opportunistic predation, 2 or 3 to the acid rain poisoning of the water sources they depended on. The survivors are thin, visibly thin. The prominent hip bones of the hadrosaur, normally smoothed over by thick layers of muscle and fat, are now creating visible ridges beneath the skin. Their movements are slower, their responses to threat less explosive, their social cohesion almost completely dissolved. They are still eating. The food they are finding is not the lush, productive vegetation of the late Cretaceous spring. It is dead and dying material, fallen leaves, the last of the seeds from before the impact, the roots of plants that are barely clinging to life in the cold soil. It is keeping them alive, barely, and the caloric content of what they are finding is decreasing week by week as the reserve stocks of chemical energy in the soil and the vegetation are progressively drawn down. The subadult Tyrannosaurus has been following them for 3 days. It is waiting, not with strategic patience, not in any conscious sense, but with the evolved patience of a predator that has learned, through millions of years of selection pressure, that a weakened prey animal is worth waiting for. It circles the periphery of the herd, reading the individuals, assessing their condition in the way that predators assess prey, through subtle cues of movement, of posture, of the particular quality of an animal that is close to its physiological limit. The opportunity comes on the 3rd day. An older male at the edge of the herd, already emaciated, goes down on one knee as he attempts to climb a low bank to reach some dried vegetation at the top. He cannot get up. His legs, stripped of muscle mass by weeks of caloric deficit, do not have the strength to lift his body, still weighing perhaps 2 tons even in his reduced state, back to standing. The Tyrannosaurus moves. The kill is quick, and the Tyrannosaurus feeds and is sustained for a few more days, and the mathematics of the collapse are delayed for it by exactly that much. 2 months after impact. The surface of the Earth, seen from above, has changed color. The deep greens and varied browns of the late Cretaceous landscape, the dark resinous green of conifer forests, the brighter green of angiosperm canopy, the gold and ochre of the floodplain grasslands and fern meadows, have been replaced by a palette of gray and brown and the pale, sickly yellow of dead vegetation. The forests are skeletal. The canopy trees have shed their leaves, not in the orderly hormonal senescence of a deciduous tree responding to seasonal signals, but in the catastrophic, uncontrolled leaf drop of trees that are dying. The leaf litter beneath them is deep and wet and cold, and it is already being colonized by fungi, the great decomposers, the organisms that break down dead organic matter and return it to the nutrient cycle, the organisms that, uniquely among the primary producers, are thriving in this dead world. The fern spike is underway. In the clearings where the trees have already died, in the open areas along river margins where the cold wind has desiccated and killed the vegetation most efficiently, a thin green is returning. Not the rich green of a healthy forest, a sparse, low-growing, early colonizing green, the first fronds of ferns pushing up through the gray leaf litter. The ecological pioneer species, capitalizing on the collapse of the complex ecosystem that previously excluded them through competitive dominance. The fern spike in the geological record is not merely a curiosity. It is a timestamp, a biological marker of devastation. And it is found consistently in KPG boundary sections on every continent where the rocks of this age are preserved. Scientists studying sites from New Zealand to Canada to Spain have found the same pattern: the sudden dominance of fern spores immediately above the KPG boundary, lasting for a period that researchers estimate at somewhere between a few thousand and tens of thousands of years before more complex vegetation begins to recover. A few thousand years. That is how long the post-impact landscape remained in the ecological equivalent of ruins, populated by ferns and fungi and the small, burrowing, seed-eating omnivorous animals that could survive on the margins. 3 months after impact. The large dinosaurs are mostly gone. Not all, not everywhere. There are survivors, isolated populations in ecologically unusual situations, animals that have found the right microhabitat, the right food source, the right combination of circumstances to persist a few weeks or months longer than the rest. In valley systems where thermal inversions trap slightly warmer air, in coastal areas where marine food resources supplement the dying terrestrial food web, in riparian zones where decomposing organic matter in the water sustains small food webs that extend just far enough up the chain to feed a juvenile hadrosaur or a small theropod. But these are the last embers. The fire is out. The Triceratops does not die dramatically. It does not die in a predator attack or a flood or a fire. It dies the way most large animals die, in a famine. Slowly, over days, as the last energy reserves are exhausted and the body begins consuming itself, and the muscles weaken, and the animal goes down and does not rise again. Its body lies in the gray landscape of the dying floodplain, covered by a thin film of cold rain, and the fungi begin their work, and the small mammals and birds and surviving reptiles come to it and take from it what they need, and continue. The Tyrannosaurus lasts longer. It lasts longer because it is the apex predator, and because it is large, and because it can go further between meals, and because it is ruthlessly efficient at finding the last remaining prey. But the last remaining prey is eventually too sparse to sustain even the most efficient and wide-ranging of hunters.
Research into the ecology of apex predators and collapsed ecosystems, including modeling studies based on the relationship between predator biomass and prey availability, suggests that in a food web collapsing at the rate the Hell Creek ecosystem was collapsing, the apex predator populations would crash within months of the initial collapse of the herbivore base. The last Tyrannosaurus rex to walk the Hell Creek floodplain does not know it is the last. It walks and hunts and fails to find prey, and walks further, and its body draws down its last reserves, and it goes down in the gray mud of a river margin on a dim afternoon under a sky the color of ash. And that is the end of the most successful large land predator in the history of the earth. Not with a roar, not with a battle, with a slow settling into cold mud on a gray day in a world that had run out of light. The small mammals are still moving in the undergrowth. The birds, those that survived, those whose ancestors would eventually fill every ecological niche vacated by the dinosaurs, are still present in the skeletal remains of the forest. They are thin. They are under stress. Many species of avian dinosaur are dying too. The large-bodied birds, the herbivorous birds, the birds dependent on specific fruit or insect resources that no longer exist. The extinction does not spare the birds entirely. Most of the bird lineages of the late Cretaceous will not survive into the Paleogene. Only a small number of lineages,
those that proved capable of surviving on seeds, on detritus, on the diminished but present resources of the post-impact world, carry through. Those survivors are your sparrows, your pigeons, your eagles and owls and penguins and parrots. Every bird alive in the world today is the descendant of an animal that survived this. Every living bird carries in its genome the memory of what the sky looked like when the ash was still falling. 6 months after impact.
The light is beginning to return. Not fully, not suddenly, but the stratospheric loading of dust and sulfate aerosols has been slowly diminishing as particles fall out of the stratosphere, as the sulfate aerosols grow large enough to precipitate, as the injection of new material from wildfires decreases as those fires run out of fuel. The process is measured in months, and the return to something approaching normal light levels takes years rather than months. But the trajectory has shifted. The darkest days are behind the Earth, though the coldest days may still be ahead, as the ocean heat reservoirs that buffer surface temperature begin to exhaust the warmth stored before the impact. But the ferns are growing. The seeds that survived the impact in the soil, the chemical energy packages that plants deposit as their long-term reproductive investment, are germinating. The fungi, having consumed enormous quantities of dead organic matter through the preceding months, are releasing nutrients back into the soil in forms that plant roots can absorb. The recovery is beginning. It will take 10 million years to fully replace what was lost. 10 million years before the diversity of terrestrial vertebrate life approaches anything comparable to the late Cretaceous. 10 million years of evolutionary work, radiation, diversification, specialization, the filling of empty ecological niches by whatever lineages were fortunate enough or generalist enough or small enough to survive. But in the cold, dim spring of a world 6 months past its worst catastrophe, something extraordinary is happening in the underbrush of the dying forests and the new fern meadows. The mammals are coming out. Not in any dramatic sense, not with any fanfare. Small, furtive, still mostly nocturnal, still wary in the way of animals that spent 66 million years being prey rather than predators. But they are eating well by post-impact standards. The seeds are sprouting. The insects are beginning to recover. The most resilient species, those with eggs or pupa buried in soil or wood, are beginning to emerge into a world where they face none of the ecological competition that previously constrained them. The fungi are everywhere. The small mammals, with their omnivorous generalist diets and their ability to eat almost anything organic, are well positioned to exploit every one of these recovering resources. They are still small. They are still unimpressive. You could hold most of them in one hand. But the dinosaurs are gone, and the world, for the first time in 165 million years, belongs to whoever is willing to take it. These recovering resources. They are still small. They are still unimpressive. You could hold most of them in one hand. But the dinosaurs are gone, and the world, for the first time in 165 million years, belongs to whoever is willing to take it.